Self-reduction. Self-reduction is an algorithmic technique to solve certain computational problems. For example, let us consider the click problem. We are given a graph and want to know if it contains a set of, let's say, at least 20 vertices, which are pairwise adjacent. When we look at the graph, we might see that it contains an isolated vertex. An isolated vertex is one that is not adjacent to any other vertex. If we see such a vertex, we can remove it, because it cannot be part of a click. In general, to apply self-reduction, we have to partition the problem instances into two cases. The first case is a reducible instance. In our example, this would be a graph that contains an isolated vertex. After we remove it, we obtain the reduced instance x prime. Then we recursively apply the self-reduction algorithm again. With the solution that we obtained from this, we solve the original instance. In this example, if we ask for the existence of a click with a certain number of vertices, then the answer y prime is also the correct answer for the original instance x. Or stated differently, removing isolated vertices from the graph does not affect the answer to our problem. Eventually, we will reach an instance that cannot be reduced any further, and then we have to solve it directly. In this example, an irreducible instance would be a graph which does not have any more isolated vertices. Unfortunately, the click problem for graphs without isolated vertices is just as difficult as the general one. So the proposed application of self-reduction doesn't really help in this case. Let us look at some better examples where self-reduction is effective. The first example is to determine if a graph is acyclic. The instance x here contains a cycle. Look at the top right vertex. Notice that it doesn't have any outgoing edges. This implies that it cannot be part of a cycle, because where would you go next if you reach that vertex? So we can delete it. Now look at the bottom right vertex. This one has no incoming edges. Therefore it also cannot be part of a cycle. Again, we can delete it. So the reduction in this case is to remove vertices which do not have at least one incoming and one outgoing edge. Then we get the following reduced instance x prime. Notice that the top right vertex now satisfies the deletion requirement as well, so we can remove it. And we apply the reduction again. Now we have reached an irreducible instance because no vertex qualifies for deletion anymore. Observe that a graph is acyclic if and only if the resulting irreducible instance is the empty graph, meaning all vertices have been deleted. If x0 isn't empty, then the remaining vertices must all be part of a cycle. If we implement this, we get a linear time algorithm to check whether a graph is acyclic, and it even tells us what vertices are part of a cycle if there exists one. Our next example is to check whether a formula has a satisfying assignment. The circled plus stands for the exclusive OR. The idea here is to select a variable and plug in 0 and 1 for it. If the formula f is satisfiable, then at least one of these two new formulas must be satisfiable as well. So if we plug in 0, we get the following. And after simplification, we can see that it is equivalent to 0. If we plug in 1, we get this formula. And after simplification, we see that this is equivalent to not x2. So the reduction is to plug in 0 and 1 for the first variable and then minimize or simplify the formula. Since no variables are left in f0, it is irreducible. So we continue with f1. If we plug in 0, we get 1 as irreducible instance. This means f is satisfiable, and the index of this formula, 1, 0, is the satisfying assignment for our formula f. So in general, a formula f is satisfiable if and only if the reduction tree contains a leaf whose irreducible instance is equivalent to 1. Our last example is the task of enumerating all permutations of a given size. Suppose we want to find all permutations with 3 elements. If we are given a permutation on 2 elements, we can extend it to one with 3 elements by inserting a 3 at one of the following 3 positions. The expression below means to insert 3 in the permutation 1, 2 at the first place, and here at the place 2 and at place 3. If we do this insertion process for every permutation with 2 elements, then we get all permutations with 3 elements. The reason for that is as follows. So there are 3 faculty different permutations with 3 elements. And this is the same number of different permutations that this algorithm returns. 2 options for choosing one of the permutations with 2 elements, and 3 options for where to insert the 3. So the set of all permutations with 3 elements can be expressed as follows. First, choose a permutation with 2 elements, and then choose a position where to plug in the 3. In general, the 3 becomes n, and the 2 becomes n minus 1. The irreducible instance in this case is n equals 1, for which we simply return the set of all possible permutations directly. So this concludes our short introduction of the self-reduction technique. I suggest that you try to implement these 3 examples in a programming language of your choice to see if you were able to comprehend the ideas.